Okay, ready to go.
So I'll let Ted describe the data, and then I'll
Sure.
walk.
Yeah, so we took the data from the IPUMS higher education, and we stripped specific variables from the year 2013, and the most important ones that we thought were the like age, race, gender, salary, to kind of like have a cohesive narrative, trying to have like a solid relationship between the variables. So so we did our synthesis like sequentially. I think starting with we figured out the age through the birth year after fixing the intervals. Then we went through like the race to see how race might predict the degree, which then use all of it to predict the salary. And
a little bit of background too. It's data's like from 2013 only on people who graduated in a STEM field. So you don't have to like still be working in a STEM field or whatever, as long as you got whatever. I couldn't find their precise qualifications for a STEM degree, but if you were reported as having a bachelor's degree or higher with
STEM background,
degree, you qualified for the data set. And then obviously like degree takes on different values too. You got like graduate degrees, STEM fields. So the synthesis model Ted touched on. So like one of the ways we wanted to smooth over the age, because if you had a particular like you knew someone with a doctorate degree of a certain age and a certain race within this data set, like there's identification risks. So one way we wanted to smooth over the age without like altering too much the underlying distribution of ages is we use the fact that there is a birth year category and an age category. So essentially like this looks kind of grisly, but all it is we within your 5-year birth year window, we would just take a uniform draw. So one of those years. So if you were in the 1980 to 1984 birth year window, like you may have a true birth year of 1983, but we just sort of perturb it by drawing uniform on 1980 to 1984. And so that way, like the underlying like generational differences in the data were preserved, but not, but like a person's specific age was able to be perturbed. And then drawing for they called the column race eth for race or ethnicity. And that was just a pretty straightforward multinomial Dirichlet model. So like we used the observed counts to drive the Dirichlet prior. So that's wasn't like, there weren't any other covariates in this model. It was just a pretty straightforward multinomial Dirichlet. And I would say like race ethnicity was kind of the first real variable we synthesized, not just perturbing like we did age. And then the next one was degree, and as you see here, degree took on 4 values. And so for that, we used the multinomial logistic regression, very similar to what's been presented in class. I go back one more, sorry. So there, the predictors were gender, race, and age for what degree you had. And kind of one thing, if we were to do this again or do it with a little more computing power, we had each parameter in the multinomial logistic regression got an independent prior, and like the log normal draws were taken with a independent prior on the standard deviation. And ideally, we'd like to do this multivariate normal. So like propose all of the coefficients at once. And that way, that would allow for a variance covariance matrix that might capture like correlations, covariance between the predictors we had. We were just because of computing limitations, we had to assume they were independent, which isn't unreasonable, but like I think a more exhaustive model would allow for those relationships. So then I'll go back to salary here. So salary was top coded, and we thought this was kind of the most sensitive of the variables. So if you made less than 150,000, they just reported your salary as is. If you made more than 150,000, it was just rounded down to 150,000. And then there were some cases where either respondent refused or there was reason not to report salary, in which case he took like nearly $1 million. So really, salary was simultaneously categorical and continuous. There was one category being the continuous salary, the others being like top coded or omitted. So to do salary was synthesized in kind of a two-part process. So first we did another multinomial logistic regression using log age, gender, race, and degree to define the category. Like, were you top coded, omitted, or reported as is? Identical multinomial logistic regression structure. And then for those that took continuous salary, I think we talked about this maybe two like updates ago. Then we used a just standard multiple linear regression. So like if you got the continuous one, then you do one more linear regression in the synthesis. Otherwise, you just like if you got, say, your salary was 160,000, it would be rounded down or predicted to be in the above 150,000. It would round down and you're done. But if your salary was in the continuous, then you'd have to like go take a draw from the multiple linear regression. So that's how we got around like the simultaneous or the truncated, I guess, salary variable. And then the synthesis happened pretty much in the order I just described. I kind of always think of it as working outwards. I don't know if that's the right way to think of it. So then, Ted, you want to talk about scoring?
So the interval overlap, we didn't actually do as an estimate. We just kind of compared the range of the synthesized and original data, because just like a quick check. I didn't really want to use the estimate because we had the other measurements that I thought were more effective for a large data set. So yeah, the overlap was really close to 1. If you round it up by like the 1,000th digit, it's basically 1. But so the propensity score, seeing how well we can differentiate like a data point from the synthesized one and the unsynthesized one, we use the logistic model below that's marked. And so previously, I kind of had an oversight of trying to sort the variables into like continuous or categorical. So Isaac helped me go through that and just fix it. And so our propensity score lowered drastically. It used to be closer to 0.25, which was the upper bound, but as you can see, it dropped down to like 0.0001. So that's really good. And then just
the thing is, like you see in the bottom of the LME notation, that like you have to tell. When we started telling the logistic regression, like if you just give the salary row as is, it'll think all of them are continuous, including the like 150,000s. But if you tell the logistic regression model 150,000 really represents a category, then it has much more difficulty identifying between the two data sets. So that was one. When you have that's like one, I don't know, way of like one sort of adjustment you have to make to our readings when you're dealing with the hybrid variables.
Yeah, because previously I thought that the high propensity score was just from the fact that it was like multi-variables, like using many variables for the logistic regression. But while the ECDF was just, we took the empirical CDF of the salary, which we thought was the most sensitive and probably the best to compare. So with the squared distance, it's really small, and the absolute difference was even smaller. So it seemed really good. We weren't able to do the cluster scoring still, just because of the computing power, and we didn't sample from our data set in order to just see if it would run or not. So if we were to do this again, we'd probably do that or somehow get more computing power.
I think maybe, I don't know if there's literature out there on like using not hierarchical clustering. Just
Yeah, different models too.
Distance matrices, something of this size. And then real quick, so I think it was mentioned a couple classes ago, but it was probably like the most interesting update to our presentation, was how we did expected match risk for the like partially categorical, partially continuous variables. So Professor Hu mentioned last time, like, first of all, if the original data is categorical, you're looking for an exact match. And then if it's in the continuous category, you want to be within some like scaled radius. So we set radius having 5% to either side. And this one took quite a while to run just because we were looping over like 100,000 rows and evaluating a number of conditions. But what you see here is instead of so like with the continuous modification on the expected match risk slides, right? You're evaluating, is the synthetic data in some radius about the original data? So for us, there's kind of like three cases when defining that radius. So again, if the original is categorical, the radius should just be 0 if you're looking for an exact match. And then one other case would be the original record is continuous, but like if you were to take the radius of 0.5, the magnitude of the true value to either side, you could accidentally like catch a bunch of 150,000s, which are meant to be categorical in your radius. So you have to check, that's what you're doing here, like would the radius we've defined accidentally catch those? And then if not, move the right bound down to just beneath 150,000. And then like obviously you don't have to worry about going beneath 0. And if your proposed radius doesn't catch 150,000, you can just take it as is. And then you just look at, you know, how many of the continuous variables are in the radius, are the discrete variables in the radius, and that's your counting function. So that code's on the GitHub. Just kind of like a modification. You can talk yourself in circles trying to set this up. That was our like modified expected match risk. So that's kind of our model. I think with more time and a little more power, like maybe do more variables, try to include more years, but
all right, thank you. And